Hello everyone, welcome back to the episode 9 of the number series. For today's video, we will be talking about the Euler's function, the Euler-Tottian function, phi n. I need to point out that this formula over here, phi of n equals to n times 1 minus all of the prime factor here. This one is a better version of formula than this one here. It's much easier to calculate. Okay, let's begin. So question number 1, we will have to find the phi 42, phi 420, and phi 4200, and we need to apply this formula over here, and 42 times 1 over 2 times 2 over 3 times 6 over 7. Basically all of the prime factors times the number itself, and that's how we calculate it. And yeah, just apply the formula and you should get a result very easily. Okay, let's jump into question number 5 and 6. We need to calculate the value of a to the power of 8 modulo 15, and for a equals to 1 to 14. And question 6 is also very similar, so I will combine them together into one question. So if a and 15 they don't share any factors, then it's going to be 1 according to the property of Euler-Tottian function, because phi 15 is equals to 8 And after we put down those 1 over here, if a is having a factor of 3 with 15, and then we first calculate this by brute force, and since 6 to the power of 8 equals to 2 to the power of 8 times 3 to the power of 8, then because we know that 2 to the power of 8, it has no common factor with 15, so it's equal to 1, leaves us with only 3 to the power of 8, and which is exactly the same. And you can use this technique here to calculate those different numbers that share some kind of factors. A very neat technique here. And similarly here, if a does not share any factor with 16, which means that a equals to a odd numbers, then it's going to be 1. Okay, otherwise it's going to be 0, because if it has a factor of 2 to the power of 8 is a multiple of 16, right? So it's just 0. Question 7. Show that if n is odd, then phi for n equals to 2 times phi n. Okay, so we know that n is odd, so it has no factor of 2. So 4 and n, they don't share any factors, and we can just split them out here, and we know phi 4 equals to 2, and that's how we get phi of 4n equals to 2 times phi n, 8. Perfect numbers that satisfy that the sum of the divisor of n equals to 2n. What kind of n satisfy phi n equals to 2n? But by the definition, we know that phi n is the number of numbers that is less than n and greater than 0. At the same time, also has no common factor with a other than 1. So there's most n different candidates out there, and we know that it's less than or equal to n, which means it's impossible to equal to 2n. So this is impossible. So question 9. So we observe those little sequence here, and we need to conclude a series. So we know that the sum of all the numbers that's co-prime to a specific number and less than that number has a sum of this, because it is symmetrical. If we have a number k is co-prime to x, then x minus k and x, they are also co-prime, then it is symmetrical. We can pair them up, and there are a total of 5x numbers. That's why we get the sum of this. Okay, so the sum of the so for each different prime over here, we know that the sum of the divisor of p is equals to p plus 1, and phi p equals to p minus 1, excluding p itself. Or other things, it has no factor with p. And dp, there are two factors, 1 and p, right? So they are all the same. Then adding all of the p together, it's just still be the same. For each individual p, they are going to be the same. And question 11, prove the lemma 3 by starting with the fact that there are some number integer r and s, that ar plus ms equals to 1. So lemma 3 here is here. A and m, they don't share any factors. A is congruent to b modulo m. Then b, m share no factors. So we start with this. AR plus ms equals to 1 because they are co-prime. And also due to this congruence, we can get that a minus b equals to km. And we substitute a with the expression with b, and we get that b and some kind of number here, m, they equals to 1. That means b and m, they are co-prime. Question 12. So if a, m, they don't share any factor, show that any x such as this satisfy as congruence to c modulo m. So because a and m, they don't share any factor, we times a, and we don't need to worry about the modulo because they are co-prime. And then now it becomes a to the power of phi m, which is just equals to 1 because a and m, again, they don't share any factors, and we got this. Question 13, let f of n equals to n plus phi n divided by 2 show that f of n equals to phi n for n equals to 2 to the power of k. Well, this is just substituting this here, and we get phi n, and we get fn, and we get phi of fn, and we get fn. Yeah, and we check that the result is indeed phi n. And 15, find 4 different solutions for phi n equals to 16. Well, we know that using the formula, the numerator is going to be a divisor of the number 16 here. And that's how we pick 1 over 2, 2 to the power 2 over 3, and also 4 over 5, and 16 over 7 is just some examples, and you're gonna solve those equations here. Alright, I believe that's not going to be too hard given those, and solve for n, and we got those 4 different numbers here. There are a lot of different numbers here, so if it's different from my answer, it doesn't necessarily mean you are wrong, because there are so many solutions here, and it's probably not going to be the same number as I did. So, okay. So question 15, find all solution for phi n equals to n and prove there are no more. So suppose there's only one factor here. So prime factor 2, 3, 5. And we all know that if any prime number goes anything that's higher, then it's just going to be higher than 4. So we don't even need to consider them. And we got those. As we also know that as the same prime factor has a larger power here, that means the phi of that number is going to be higher. So we don't need to check any number that's beyond those, okay? And if there are two numbers, we pick two from we pick each one numbers from each two rows, and we get 12 and 10 that satisfy the condition. So in total, there are 4 different solutions, namely 5, 8, 10, and 12. Question 17. So show that if m and n they share a factor of 2, imply that phi mn equals to 2 times phi m times phi m. So this is phi m. Okay, sorry. So question, this is, wait, did I not cover question 16? Okay, we're gonna do 16 first. So phi mn is greater than phi m times phi n if they have a common factor. So we know that phi m, this is phi m, this is phi n, and if they do share some kind of factor prime, then phi mn is just going to combine those two together into one single thing here instead of the power of 2, which result in larger numbers. That's why phi mn is going to become larger. Okay. Question 16. So this is phi m and this is phi n. Just notice that, keep in mind that the factor of 2, the power. And so k1 and k2, they are the largest power of 2 for m and n. Notice that this is the power of factor of 2, and phi mn equals to this, which we have a power of this. Okay. And yeah, so according to these, we can deduce that if we times 2 to the product of phi m and phi n, we get phi mn. So question 18 shows that phi n equals to phi over 2 only if 2 to n equals to 2 to the power of k for some positive integer k. So if phi n equals to n over 2, then we know that this part over here is equal to 1 over 2 here. And in order for the denominator to have a factor of 2, there must be a 1 over 2 over this product, because all other prime, they have no factor of 2, okay? And since all other small fractions, it's just going to make the product even lower. So if we have any prime factor, it's going to be less than 1 over 2. It's not equal to 1 over 2. Therefore, 1 over 2 is the only factor. That means 2 is the only prime factor of n. So n have a form like this. So question 19. If n minus 1 and n plus 1, they are both prime, then phi n is less than or equal to n divided by 3. So we know that this is 3 consecutive numbers, right? So there must be one of the multiple of 3 among them, and those two are prime. They don't have a factor of 3. That means the factor of 3 must lie in here. And this is odd, this is even, this is odd, so this is even. So it has a factor of 2 and 3. So using the formula here, we know that here, other prime factor is just going to make n even smaller. So, okay, so add here. So it is at most n over 3 here. And I think that's not too difficult to understand. And question 20, so phi n equals to 14 is impossible. Well, we observe those prime factors and their corresponding denominators. And we know that if n ever have those different things here, n is able to divide out those of denominators, which means that the number in the numerator is a divisor of n. The divisor of phi n, sorry. And any prime number that's larger is going to have a very larger number in the numerators, which makes things phi n is greater than 14, so we don't need to consider any more numbers. And we know that 3, okay, so those 3 numbers, they can be because it has a factor of 3 here. And okay, so this numbers here, it has a factor of 3. And it's going to become a factor of phi n, which 14 it does not have a factor of 3, so this is impossible. Which means that n is not a multiple of 7. But we observe that those numerators, they don't have a multiple of 7s. So there's no way for us to get a multiple of 7s for the phi n, because either the factor of phi n comes directly from n, or it comes directly from the numerator here, but we don't have any multiple of 7 here, which means this is impossible. And we finish our section today here. Thank you everyone for watching me talking about those different math problems for so long, and see you in the next video. Bye.